I think this question was not solved. Maximum pressure difference between inner and outer surface of a thin-walled circular tube of radius r and thickness delta r so that it won't break. The breaking stress is sigma naught. Could you solve this?
Sir, answer is del R sigma naught by R.
Del r sigma naught by r, yes, that is the answer. Okay, so let us try to understand that suppose this is the thin walled cylinder. Cylinder means it's a pipe like thing, like this. It's a tube. Alright, so let us assume one small cross section, which is this one. This cross section I will draw its free body diagram. Right? If I draw the free body diagram of this cross section, you will see that the front view I'm drawing, I'm trying to draw the front view only. The front view, it will look like this. Right? And this is the length of the tube. Suppose the length is L. This is the side segment cross section, side cross section. Now, as it is the external pressure is more than the outer side pressure, so let us assume the extra pressure that is acting inside the tube is delta P. So if the extra pressure is delta P, then the force that this extra pressure is exerting on the tube surface is in upward direction, right? What will be that force? Pressure multiplied by area. If I use this angle to be delta theta, then can I assume this area in a rectangular shape? Can I assume this area to be a rectangular shape? The length of this rectangle is L and this width is R into delta theta. Yes or no? So the force by the excess pressure is delta P multiplied by R L into delta theta. Right? And what is the tension force? Where the tension force is acted? Can you see the tension force is acted tangential to this surface? They are actually acting from this side. Yes or no? Can you visualize the tension force that I have drawn here? The
Yes, sir.
tension force that I have drawn here. Now, what are the vertical component of the tension force that I have to calculate? Because that vertical components are only responsible to balance this vertical force. Yes or no?
Yes, sir.
So it's very simple. As delta theta is very small, can I say it is t into sine delta theta by 2?
Yes, sir.
And it is also t into sine delta theta by 2. The resultant of these two forces are balancing this force due to extra pressure. So T into delta theta is equal to P into delta P into L R into delta theta. Right? So I can say that what is tension is equal to delta P into LR. Now, in order to find out the stress, I have to divide area with the tension. Tension divided by area. Stress is tension divided by area. Now, which area I will choose here? You can see the tension is acting perpendicular to this surface area that is colored to this red. Yes or no? Tension is acting perpendicular to this side area.
Yes.
So if I have to calculate the normal stress, then which area I will divide with the tension?
L into delta R.
L into delta R. Yes, because this thickness is delta R, this thickness is delta R, and this side length is L. So L into delta R, and that stress should be less than sigma naught in order not to break it, right? So delta P into L R divided by L delta R is less than sigma naught, which will give you that excess pressure should not exist. Excess pressure that should be less than sigma naught into delta R divided by R. Have you got it? Yes. Have you found the solution of this question? Okay. Have we done this question?
No, sir.
A steel rod of cross section area 16 centimeters square. Steel rod of cross section area 16 centimeters square and two brass rods of cross section area 10 centimeters square together supports a load of 5000 kg. The stress in the steel rod will be, what is the stress in the steel rod that I have to calculate? You can assume that 5000 kg block always remains in horizontal position. Have you got the solution? Anyone got the answer? Look, this 5000 kg has to be supported by these three rods. So suppose the force by this rod, force on this rod is F1, this rod is F2, and this rod is F3. And F3 and F1 both are the same because they are symmetrical. And this is also F1, F2, and F1. Right? If this remains at rest, then whatever may be the elongation or compression here will be the same for both of them.
Yes.
So for the first one, F1 by A1 is F1 by A1 is, yes, F1 by A1 for the first case F1 by A1 into Y1 is equal to delta L1 by L1, and for the steel rod F2 divided by A2 Y2 is equal to delta L2 divided by L2. So one more equation we know that delta L1 is equal to delta L2 and F2 plus 2F1 is equal to 5000 kg, means 5 into 10 power 4 Newton. Can we write these equations? Just check if the equations are correct.
Sir, why would the compression be same for all the three rods?
If the compressions are not same, then the bar will not be horizontal, right? This bar will not be horizontal,
Oh, okay, sir.
right? So in this type of diagram, always you have to consider the situation to be in horizontal.
Sir?
Yes.
Sir, will there be any problem if the bar is not horizontal?
Yes, if the bar is not horizontal, then how you can solve this question? Then you cannot solve this question. They may have different compressions and you do not know any relation between their compressions. You should know the relation between their compression. If it is not horizontal, then you should know the angle or something you should know. Otherwise, you can't solve it. Right? But look, this type of situation, it is a practical situation. As I've told you that these are used in several constructions. So if it is a construction and if it is a overhead bridge or something like this, so you will never want that this bridge will incline at certain angle, right?
So if they remain in contact, then the compression must be same.
Yes, that I have done. The compressions are always same. That I have done only. The compressions are same. Right. So delta L1 equal to delta L2. If I find, then what equation I will get? F1 into L1 divided by A1 Y1 is equal to F2 into L2 by A2 Y2. Now I can find a relation between F1 F2 from here, right? So F1 is equal to F2 into L2 by L1 into A1 by A2 into Y1 by Y2, right? So F2 into L2 by L1, L2 by L1 is equal to 3 by 2, I think, right? 3 by 2. A1 by A2, brass divided by steel, cross section area, brass rod has 10 and steel has cross section area 16. So 10 divided by 16. Y brass by Y steel. Y brass is 1 into 10 power 6 and Y steel is 2 into 10 power 6. Y steel. Right? I think we have found a relation between them. 15 by 32. F2 into 15 by 32. Now if I find this F1 and F2, I have to find the stress in steel rod. F2 I have to calculate. So F2 plus 2 F1, F1 is equal to F2 into 15 by 32 is equal to 5 into 10 power 4. So it is 16, right? So 16 plus 15, 31. So F2 is equal to 16 by 31 into 5 into 10 power 4. Then the stress in steel is equal to F2 by A2. Right, F2 by A2. F2 means this one divided by A2 means cross section area is 16 centimeters square. Right, steel rod has a cross section 16. So is the answer is Newton per centimeter square. So I think it is 5 by 31 into 10 power 4. 5 by 31 into 10 power 4 Newton per centimeter square. Now approximately how much it will be? 5 by 31 can be approximated to 1 by 6. Right, 1 by 6 means I think option A should be your correct choice. So I think this point will not be there. Right, these points will not be there. Then this will be your correct answer of this question. Okay, so these are calculation based question. You can understand. Next, we'll talk about elastic potential energy. Very important thing. Before going to elastic potential energy, let us find equivalent spring constant. As I have told you earlier, that all the bodies behave as a spring. So if I calculate the equivalent spring constant, I can find the force or the energy just by the spring equations. Force equal to kx or energy equal to half kx square, like this. So suppose there is a rod. Suppose there is a rod of length L. By applying a force F, tensile force definitely, the rod has been elongated by elongation delta L. We say that F is equal to A into Y into delta L by L. Yes or no? F by A equal to Y delta L by L. If I compare it with a spring that has natural length L and I elongate it by a force F, further elongation delta L, spring constant is K, then can I say F is equal to K delta L? If I compare these two equations, you can see that the equivalent spring constant of this rod is A into Y by L. Equivalent spring constant of this rod is A into Y by L. Right? That is why also we have done one thing in spring. I think if you remember or not, that if we cut a spring, how do I find spring constant? Suppose a spring of natural length is L.
K1 L1 equal to K2 L2.
Yes. If the natural length is L, suppose I have cut the spring in two parts of ratio say 1:2. Then if the natural length of the spring is L0 and spring constant is K, now K1, K2 can be found by this way. K1 into L1 is equal to K2 into L2 equal to K into L0. Spring constant into natural length, it is equal to A into Y. Now area and Young's modulus are constant for this material, but lengths and spring constants are not constant. So K1 is equal to what is L1? L1 is equal to L by 3, right? So it is 3K, and K2 is equal to 3K by 2, right? So you know that spring constant into natural length is a constant. In that way we calculate the spring constant if we cut a spring, right? From here actually it is coming. So if I now know what is the equivalent spring constant, then I can also calculate what is the energy, potential energy stored in stretching a rod. Potential energy is equal to half kx square, half k delta L square. Just if I replace it like this, it is half into k delta L by A, k delta L into delta L by L into A into L. Look, can I modify this equation like this? K delta L square, K into delta L square into AL by AL. Now what is K delta L by A? Is it F by A?
Yes. Yes, sir.
Delta L by L is strain and A into L is volume. So energy stored is equal to half into stress into strain into volume. Right? Or energy density is equal to half into stress into strain. Can I also write energy density is equal to area under stress strain graph?
Yes, sir.
Because we only consider inside proportional limit where stress and strain are straight line. The function is straight line. Stress strain. So what is area under this stress strain graph? Half into stress into strain. So energy density is equal to half into stress into strain, or it is area under stress strain graph. Right? That you need to remember. One question is this one, a very important question. A rod of mass m length L hangs from the ceiling. Find the elongation of the rod due to its own weight and what is the elastic potential energy stored. Young's modulus is given. Suppose this is the rod. And if you talk about this cross section, small cross section, you can see that only tensile stress is due to the weight of the lower part, right? It is being stretched due to this lower part. Upper part cannot stretch it, right? It is free to move in downward direction. So it can be only stretched due to this lower part, right? So this is dx, suppose this is x, This is dx. So it is stretched by the weight of the lower part, right? So that force is equal to mg by L into x.
Yes.
So the stress is mg by Al into x. So what is strain? Strain is dx by dl. I'm sorry, dl by dx. dl is the elongation of this small dx part. That is stress by y. dl is elongation of dx part. So dl is equal to mg by Al into x dx. X equal to 0 to L. If you integrate, you will find that delta L is equal to mgl by 2ay, right? Second part is the energy. This small segment has energy which is equal to half into stress into strain into volume, half into stress into strain into volume. So that is equal to half into what is stress into strain
mg by L.
is equal to stress square by y, you can say, right? Stress square by y. So m square g square by a square L square y into x square into volume is equal to adx. Can I write it? Then while integration, I will find my answer from 0 to u, and x will be from 0 to L. It's m square g square by a square L square y into a will get cancelled out, al square y into x square dx means x cube by 3, right? So L cube by 6. So I think one L will be there. So m square g square L by 6ay. That will be your answer. Elastic potential energy already you have done. Have we done this question? A thin uniform metal rod of length 0.5 meter and radius 0.1 meter rotates with angular velocity 400 radian per second in a horizontal plane about a vertical axis passing through one of its ends. What is the tension in the rod? The elongation of the rod. Density of the material is given. Young's modulus is given. How do I solve this question? Suppose this is the axis of rotation and suppose this is the rod which is rotating in a horizontal plane, right? So if it is rotating in horizontal plane, then is the tension everywhere or the stress everywhere same on the rod?
No.
No.
No, sir.
If I take a small cross section of this rod at a distance x from this end that has a small thickness dx, then I will only focus on this small portion, and you can see that the tension on this small portion is due to this right half or right part of this rod? Yes or no? If you equivalently replace this rod by a spring, then you can see that this is the left portion of the rod, this is a spring of length dx, and this is the right portion of the rod. So if I rotate it, then the spring will elongate, and the elongation of the spring is responsible due to this rotation, this mass. Yes or no? The right side of it. Have you got it?
Yes,
Yes,
sir.
sir.
So what is the force that right part of the rod is exerting on the spring? In order to find that, I will take the center of mass of the right portion of the rod, right? Center of mass of this segment. And I can say that if it is rotating with omega, then if this radius is r, then the force on it is equal to this small part m prime into omega square r. Yes or no? Stretching force on the spring is m prime omega square r. Can you calculate this m prime and r in terms of x and find what is the actual value of f?
So it is m omega square into L square minus x square by 4 and 12. Means down only.
Yes. M prime, you can see m prime is equal to m divided by L, m divided by L into L minus x. Yes or no? Omega square into r. What is the center of mass of this point? If this is x and this position is L minus x, so this is L minus x by 2, right? So this is x plus L minus x by 2. Yes or no? So I can say it is m omega square by L, 2L into L square minus x square. It is the force on this segment. So what is the strain of this segment? dl by dx, that is equal to strain equal to stress F by A into Young's modulus Y. Can I write it? What is dl here?
Elongation of the small portion.
Elongation of small portion. Elongation of dx. So now I will integrate dl from x equal to 0 to L and I will find my answer. Just integrate and tell me what you have got. It's m omega square by 2LAY. L square minus x square means L cube minus L cube by 3. It's 2L cube by, so 2L I get cancel. So it is m omega square L square divided by 3AY. Right? Just check. Look, the question says that at the water level the density is rho naught. The water level the density is rho naught. As you go down, the density will increase or decrease As we go down, will the density remain same or it will change?
It will increase.
It will increase. The reason is very obvious. If you take a small layer of water, suppose this layer, small layer of water, which has a particular volume and mass. Now, if you consider the water above this level, then this above this water, this level, water is exerting a force on this level, on this layer, right? So due to that stress, this is a volumetric stress. You can see that this volume will change. This uh, length will compress. As the volume decreases, although mass remains same, then density will increase of this particular layer. And as you move downward, the density will increase more as the force above it by the water column will increase. Right? So I can say that for this particular segment, any segment actually, the volume into density that remains a constant, right? Because it is nothing but mass. Whatever you do, the mass you cannot change. So I can say rho into dv plus v into d rho is equal to 0. So I can find one equation that v dv by v is equal to minus of d rho by rho. That is the relation between density and volume. Also, we know that in bulk modulus, do you remember the formula for bulk modulus?
Minus dp by dv by v.
Minus dp divided by dv by v. Right? So instead of dv by v, if I now use d rho by rho, then I will find a relation of density d rho by rho is equal to minus 1 by b into dp. Right? So I have to find pressure in terms of H, right? What we can do, density in terms of pressure we can find, and also we can find pressure in terms of density, right? One equation also is there. Do you remember, as I go down, suppose this depth is y, suppose this is the depth y. So if I find what is dp by dy from simple hydrostatic calculation, do you remember what is dp by dy?
Rho g.
It will be rho g. Yes. If we take y from bottom, it is minus rho g, but I have taken y from the top surface, so it will be plus rho g. Now look, I have two equations, right? Now I can replace this equation. From these two equation, I can find density as a function of y as well as pressure as a function of y. Right? The first I have to find density as a function of y. So in order to find density as a function of y, density at depth y, I can use this equation d rho by rho is equal to minus 1 by b into dp. Now dp is equal to rho g into dy, right? So d rho divided by rho square is equal to minus g by b into dy. I can integrate it, as it is given that initially at y equal to 0, density was rho naught, and at certain depth y, the density I do not know. So I can say 1 by, it is minus 1 by rho integration. So 1 by rho naught minus 1 by rho is equal to minus gy divided by b. I think there will be no negative sign because dv by v is minus d rho by rho. Yes or no? So this negative negative will cancel out. This will be a positive quantity only. Why? Because density will increase, right? Density will increase. So 1 by rho is equal to 1 by rho naught minus gy by b. Or look, I can also find the density as a function of y, which is equal to b into rho naught divided by b minus rho naught gy. That is the first step of this question. How do we calculate density as a function of y? As y increases, right, as y increases, this term decreases and this term actually increases. So density increases with y. Now how do I find pressure as a function of y? Pressure as y. Then I will use the same equation, and equation number 3, which says that dp is equal to b into d rho by rho, or dp by dy is equal to rho g. Equation number 4 I will use. Sorry, dp is equal to rho g dy. Rho g dy. I'll just replace rho by y function, and I will say dp is equal to b rho naught divided by b minus rho naught gy into g into dy. Right? Now if you simply integrate this equation, you will find your answer. Now from y equal to 0 to h, and from pressure is equal to P naught to P. So P is equal to P naught. Now look, dy, this term will be inside the integration. This entire term will be inside the integration. Right, so this integration, I think if I take minus 1 by rho naught g, so it will be minus b only into ln of b minus rho naught gh divided by b minus 0. So that should be your answer. Pressure at a depth h is equal to p naught minus b into ln of 1 minus rho naught gh by b. That should be your answer of this question. Have we got it?
Yes.
All right. So this was all about elasticity. We have discussed so many things in elasticity, mainly based on Young's modulus. That is very important, Young's modulus. Bulk modulus is also very important. Modulus of rigidity is not that important. Very rarely you will find any question. Rather, you will not find any question directly from modulus of rigidity. But this bulk modulus, again, we are going to use in several chapters. Right, mostly in waves we will use that bulk modulus part. There is another thing that we should know, which is Poisson's ratio. Yes, Poisson's ratio is a ratio where we have uh, taken into consideration the longitudinal strain as well as the lateral strain. What do I mean by longitudinal and lateral strain? Suppose this is a cylinder. Suppose it is a cylinder, and I have elongated that cylinder. I have elongated this cylinder. So this was the original cylinder, which has a length and radius. Right, now I have applied some tensile force on it, and due to that tensile force the length has increased, but you can see that as the length has increased, the radius has also decreased. Yes or no? It is actually a practical situation. In most of the cases, we have neglected the change in this radius because the radius itself is very small in size or the negligible in size compared to this length. So if this is the length L, by application of this tensile force, I can say that this tensile force, I can say that this length has increased by delta L. But what was the earlier radius R has now decreased by R minus delta R, right? So this decrease is delta R, right? So as length increases, radius decreases. Poisson's ratio is the ratio of the lateral strain divided by longitudinal strain. Lateral strain is delta R by R divided by longitudinal strain is delta L by L. Why I have taken a negative sign? Because delta R decreases if delta L increases, right? If length increases, radius will decrease because the volume remains a constant. This is the Poisson's ratio, right? And this is given as sigma. In this particular question, take a particular question. This question says a rod, suppose a cylindrical rod, right? A cylindrical rod of volume V is elongated by tension such that its longitudinal strain is E. Find the fractional change in volume if its Poisson's ratio is sigma. Can you tell me what is the answer of this question? What will be the answer?
But do we have to do any approximations?
Approximation you can use, yes. These changes are very small that you can use. Look, V is equal to pi r square L. R and L both are variable. So I will differentiate V and I will say pi r square L. If I differentiate it, first I will take R to be a constant. So pi r square into dl. Then I will take L to be a constant. So it is 2 pi r dr into L. Right? Actually, I have done a partial differentiation and I have added both of them. So dV is the change in that volume, but actually it is the volume, the fractional change in volume that you have to find. So actually here the volume is changing. If you understand, fractional change in volume you have to find. Right? I am not said it is zero. dV is equal to pi r square dl plus 2 pi r into dr into L. It only differentiated V. So what is fractional change in volume? dV by V, that is equal to pi r square divided by dl divided by pi r square L and plus 2 pi r L dr divided by pi r square L. So it is dl by L plus 2 dr by r. Now I know that dr by r is equal to minus E into dl by L, right? Minus sigma into dl by L. So it is dl by L minus 2 sigma into dl by L. So 1 minus 2 sigma. dl by L is given as E. So E into 1 minus 2 sigma will be your answer.